So friends, today we'll be going through frame question of applied mechanics, and this frame question holds a great importance in any sorts of examinations point of view, in any level examinations for any university of Nepal, likewise for any other university of foreign countries as well. So here we are presented a question of frame in which we have given the two hinge supports A and F, and we have presented member AB, BC, CD, DE and DF, in which a triangular load is given in section AB and of intensity 30 kilonewton per meter. So 30 kilonewton per meter intensity is given, and in section BC the uniformly distributed load of 10 kilonewton per meter has been given, and at C there is an internal hinge, and at section DE is our overhanging part. At E joint we have 40 kilonewton as an point load. So friends, we need to determine axial force diagram, shear force diagram and bending moment diagram from this above frame question. So for the complete solution, stay tuned to this video and watch the complete section of this video. So friend, for solving such type of problem, first of all we need to know the given structure is determinant or not. So if the structure is not determinant, we cannot solve the questions normally. So for that we have to know a whole lot of other features, other theorems, other techniques to solve the static indeterminate equation. So here we have two support at A and F, both are hinge support, and hinge support have two reactions as shown in the given figure. We have assumed the direction of the reaction force as such. Here, the number of available equations are 3 plus 1. One is assisted by your condition of hinge. So total number of equation comes out to be 4. And the number of reactions available are 2 plus 2 equals to 4. So the degree of static indeterminacy is the number of equations available, 4 minus 4, that yields to be 0. So this is a structurally determinant, statically determinant structure, and we will just use these summation of moment at a point equals to 0, likewise summation of force in x direction equals to 0, and summation of force in y direction equals to 0 to solve and determine the reaction forces and draw axial force diagram, shear force diagram and bend moment diagram in this section. So friends, to solve these diagrams, please watch the complete video till the end. So friends, first we need to determine the support reactions. So the support reactions that are assumed in step first, you need to determine the support reactions. So for determining the support reactions, we can use the equation of static equilibriums. So here at first we will use the summation of moment at point C, that is internal hinge, equals to 0 to the left side only. So we are just taking the summation of moment at point C to the left side only, equals to 0, and taking clockwise moment as positive. So here, so at point C, only in the left direction, just look at there. So this triangular portion, this triangular section will be giving the anti-clockwise moment at point C. So we have written minus of half into 30 is the intensity of the triangular load, into the distance is 8, and the perpendicular distance from C to the centroid of the triangular portion is 2/3 of 8. As here 2/3 of 8 is because we are moving from the apex, so only from apex or triangular edge we will always have 2/3 of that base distance is 8. So plus here r ay is making clockwise movement, so r ay into the perpendicular distance 4 minus of this. So here 10 kilonewton per meter, that is UDL, is making anti-clockwise movement, so we have written minus 10 into 4 into 2. Also RAX is also making anti-clockwise movement, so it is also negative here, minus RAX into 8 equals to 0. So solving this, we will just receive the equation 1 as 4 RAY minus 8 RAX equals to 720. So this is our equation 1. Likewise, we can do the summation of moment at F point equals to 0. Here we can do in any point, so we can do in A point or F point. So we are making the summation of moment at F point equals to 0. This has advantage as at F point we have RAX will not give any moment, RFY will also not give moment, RFX will also do not give any sort of moment. So the only reaction force RAY will be giving the moment at point F. So from this we can determine the magnitude of RAY. So this is the advantageous aspect of taking the moment at point F equals to 0. So taking the moment at F point equals to 0 and taking clockwise moment as positive, we will get RAY into 8 clockwise moment minus 10 into 4, 10, that is UDL is giving your anti-clockwise moment at point F. So it is written negative, minus 10 into 4 into the perpendicular distance is, this is 4 plus the centroid distance of the triangular, sorry, of UDL. So UDL is 4 meter, its central is located at 2 meter. So 2 plus 4 is the total distance up to the centroid from point F, plus 40 is giving here, 40 is giving here, 40 is the overhanging point load at point E, it is giving your clockwise movement, so 40 into 3 plus the triangular section will also be giving your clockwise movement. So 1 by 2 is the 1 by 2 into 30 is the total intensity into 8. 8 is the total distance into perpendicular distance is 1/3 of 8 equals to 0. Here 1/3 of 8 is there because 1/3 is the 1/3 of base distance. The 1/3 because we are moving from the perpendicular section, not from the angle. So when we will be moving from the apex, it is always 2/3, and others from the base we will be going through 1/3. So solving this, we will get RAY equals to minus 25 kilonewton. So the minus sign signifies that the assumed direction, what we have assumed in the frame direction at the reaction section, is in the just the opposite sense. That is, we have assumed RAY as upward direction, but actually this RAY is not in upward direction, it is the downward direction. So we have actually it as downward direction, but we will be substituting the value of RAY as minus 25 kilonewton in all the other aspect, because we have assumed all to be our assumption. So we will just substituting all the values that comes to be what actually is. So you need not to bother about what is its actual sense. Okay. Likewise, after taking moment at point F equals to 0, we will take the summation of forces in y direction equals to 0. So we have assumed y direction is upward direction. So upward direction as positive, taking upward direction positive, we will get minus 25 plus RFY minus 10 into 4 minus 40 equals to 0. Here, solving this, we will get RFY equals to 105 kilonewton, and 105 kilonewton is positive. We got it as positive, so our assumed direction is correct, and it is actually acting in upward direction as well. Likewise, we can, from equation 1, we can determine the value of RAX. So in equation 1, we have determined the value of ray. So substituting the value of ray in equation 1, we will be able to solve the value of rax. So here the value of rax can be obtained as 102.5 kilonewton, but it is a minus. So this minus signify that it is in the just opposite direction to the direction that we have assumed. So we have assumed rax in the rightward direction, but actually this rax will be towards the leftward direction. So this is the significance of this negative sign here. Likewise, taking summation of forces at point, taking summation of forces in x direction equals to 0 and taking rightward direction as positive, we will get minus rax plus 1 by 2, 30 into 8 minus rfx equals to 0, and solving this we will get rfx equals to 17.5 kilonewton, and this rfx comes out to be positive, and we have assumed the direction as the same as what is actually coming in the question answer. Sorry. So friends, we need to make now the balancing of all the forces and reactions in the given frame structure. So we need to balance all the sections, like we need to balance AB, BC, CD, DE and DF section. We need to balance all these sections here, and at first we need to write the directions. We need to write the directions of the reaction forces that are occurring at the joints A and F here. Here at joint A, a downward force of 25 kilonewton is acting, and a leftward force of 102.5 kilonewton is acting. Likewise, at point F, an upward force of 105 kilonewton is acting, and a leftward force of 17.5 kilonewton is acting. So we have just written, we just write the forces that are actually in the supports. So we need to balance these forces first. So first, here we will go through all the sections step by step. At first we will go to AB. In AB, 25 kilonewton is acting downward. So to balance this, a upward force of 25 kilonewton will be acting like as shown in figure here. So 25 is acting downward. To balance this, 25 in acting upward. Likewise, 102.5 kilonewton is acting towards leftward direction, and we need to balance this force here. So 102.5 kilonewton is acting, and here is a UVL. So at section AB we have a UVL of 30 kilonewton per meter. So this UVL and 102.5 kilonewton shall be balanced. So for this we will do 102.5 into 8 minus 1 by 2 into intensity of uniformly varying load 30 kilonewton per meter into the distance 8 meter into 2/3 of 8. So this will give us 180 kilonewton in clockwise direction. So to balance this 180 kilonewton in clockwise direction, we need to apply 180 kilonewton meter force, kilonewton meter force in anti-clockwise sense. So we put 180 kilonewton in anti-clockwise sense force there. Likewise, at point B, there will be the leftward force of 17.5 kilonewton, and so this 180 kilonewton force, this is the balancing force at point B. So this should be balanced by, so we have just applied this 180 kilonewton meter force, moment, 180 kilonewton meter moment here. So to balance this moment, we will apply this clockwise moment at joint B of section BC, 180 kilonewton meter, a moment we applied in BC, and we have taken 25 kilonewton in downward direction at point B to balance the upward force of 25 kilonewton in section AB. Likewise, we will balance all the sections like this. At point C, if we just calculate that, if we calculate at point C, the moment from the leftward direction or rightward direction at point C shall come out to be 0. So if you want to check it, you can check it. So this is one of the check in which you can just check your balancing force are correct or not. So likewise at section CD, there is a downward force perpendicular to the section 65 kilonewton, and to balance this 65 kilonewton we will put upward force. Likewise 260 kilonewton meter is the moment at point D because of the force of 65 kilonewton acting downward, and this 65 into 4, this is making clockwise movement, sorry, anti-clockwise movement, and to balance this we need to put clockwise movement of 260 here. Likewise in section D, so at E joint there is a downward force of 40 kilonewton, and if we calculate the moment at point at section ED at joint D, there will be this clockwise moment of 120 kilonewton meter, and to balance this we need to provide 120 kilonewton meter at this point D. So here we have this 260 kilonewton, so at point D we have this 260 kilonewton meter in anti-clockwise sense, sorry, in clockwise sense, and 120 kilonewton meter moment in anti-clockwise sense. So the net moment at point D will be 140 kilonewton meter in clockwise sense. So to balance this net moment, we need to provide an anti-clockwise moment of 140 kilonewton meter at point D in the section DF. Here we balance the section DF, so like this. So we will balance the section DF like this. So this is the free body diagram of the given frame in which all the sections have been balanced. So friends, the first thing we need to draw is the axial force diagram. So axial force is the force along the member, that is the force along the sections is the force that is in the axial force diagram. So here we have different members like AB, BC, BCD, DE, and DF. So this is the force parallel with the sections, that is along with the sections, that is the members given. So here we have in member AB a force is along the member AB whose magnitude is 25 kilonewton, and it is stretching the member or elongating the member. So it is tensile force and it is treated as positive here. Likewise in member BD, we have a compressive force of 17.5 kilonewton, and it is just making the member shortening. Likewise in member DF, we have a compressive force of 105 kilonewton. So to draw the axial force diagram, all we need to make is just draw the skeleton frame of the given questions. So we need to just first make A, B, C, D, E, F. So we need to make just a skeleton here first. Then we need to draw the magnitude of the individual member sections. So here in section AB, we have a tensile force of 25 kilonewton. So we just draw a 25 kilonewton from point A, and since it is, and we draw a straight line parallel to AB and join it to point B. Likewise, at section BD, we have a compressive force of 17.5 kilonewton, and so compressive force is treated as negative here, and we just make a compressive force, we just draw a parallel line to BD. Likewise, here in section DF, the value of force, axial force, is 105 kilonewton, and we draw a line parallel to DF having a magnitude of 105 kilonewton. So this is the way you can draw the axial force diagram. So friends, next step is to draw your shear force diagram. And for drawing shear force diagram and a bending moment diagram, we have listed a small conceptual fact that if we have a point load in shear force diagram, then the shear force diagram will be a straight line. And if you have UDL in the given frame, then the shear force diagram will be inclined straight line. And if you have uniformly varying load, we will have square parabola. So this is the thing that you have to know that. Likewise, in bending moment diagram, you must know that if we have a point load, then you have an inclined straight line. And if we have a uniformly distributed load, then you have a square parabola. And if you have a uniformly varying load, then you will have a cubic parabola. So this is the thing that you must know before proceeding to the for drawing shear force diagram and bending moment diagram. So for calculation of shear force diagram, for drawing shear force diagram, first I have just made the simple diagram here. Here in section AB, you have a one. So first you need to know what is shear force. Shear force is that force which is acting along the perpendicular directions with respect to the member. So if the member AB is your straight, then the force 102.5 is in the perpendicular directions. So this is the shear force. So this is the shear force. 102.5 is your shear force in the section AB at point A. So this shear force at point A, this is acting upward. So left up. So we need to know left up, right down is positive. So the vice versa is negative here. So left of 102.5 in section AB is upward direction. So it is positive 102.5. Likewise at point B, 17.5 is acting upward. So we have left up, right down. So left, right is again off. So this must be a negative one. So we have negative 17.5 we written in negative side. Likewise, so we need, so this nature of loading is your uniformly varying load. So at section AB, we will have a square parabola. So this square parabola, we need to know whether this moves from upward to downward or downward to upward. So we will determine the value of shear force at midpoint. Shear force at midpoint, and by that we will know the exact nature of the shear force diagram. So this is only the just skeleton. So actual diagram will be drawn after assessing the value of shear force at midpoint. Okay. So likewise in section BC. So in section BC there is a uniformly distributed load UDL, and so it is acting at point B. We have 25 kilonewton in downward direction. So it is negative because left is down, negative 25. Likewise at point C, we have upward of 65 kilonewton. So left down, right up, left up, right down. So this is again negative here, minus 65 we have. And there must be, since there is a uniformly distributed load, the angle, sorry, the nature of the shear force diagram will be inclined straight line. So 25 and 65 have been in inclined manner. Likewise, in section CD, we have 65 kilonewton. C is downward negative. We have just written there. And at point D, we have 65 kilonewton upward. So this is also what? Section D. Okay. So that in section CD there is no any low, in the given section only 65 kilonewton and 65 kilonewton is there, so it is a constant load. So it so the nature of the shear force diagram will be constant. Likewise, at section DE, there is upward force of 40 kilonewton. So it is upward. So we have positive here. Upward 40 kilonewton is positive. And at E, there is downward 40. So it is positive here. And so there is a point load. So we have a straight line as shown in figure in section D. Likewise, so friend, at section DF, we have 17.5 kilonewton acting towards rightward direction. 17.5 kilonewton acting towards right direction. So this will be our positive. And so this is a point load. We have a straight line in your shear force diagram. So this is the simple way for making the points located in the shear force diagram. Now we will just make the exact shear force diagram. For the making the exact shear force diagram, we will have to assess the orientation of the section AB, that is the square parabolic section, in which orientation it lies. For this we need to know the shear force at the midsection. So we will just cut a section of this triangular loading and determine the exact value of shear force at the middle point, and we will also determine at what distance this shear force is 0 in the section AB. So for determining the shear force at the midsection of this frame in member AB, we need to just cut the section in the triangular portion. Here we cut the section and we just put Vx in upward direction and a moment Mx. Here we need to know the height of this section Vx. So earlier it was 30 kilonewton at the highest point if it was full, but we have got a section where the shear force is Vx, and we need to know the intensity of that section. So we use the similar triangle, and so we have h by 30 equals to x by 8. So if h be the height of this Vx section, then h equals to 3.75 times x. So where x is the distance from point B along member BA. So this is the distance from point B or joint B along BA is the x distance, and we need to know. Now we will just write down the expression for shear force, then do accordingly. Now using the equation of static equilibrium in this triangular section, taking summation of forces in y direction, positive, upward direction, positive, we have Vx in upward direction, Vx plus 17.5 is again in upward direction, and the intensity in downward direction minus 1 by 2 into the height. The height is 3.75 times x into the distance x equals to 0. So solving this, we have Vx equals to 1.875 x square minus 17.5. So we need to determine the shear force at the midsection. So the shear force at the midsection is VAB mid when x equals to 4. So we have AB at 8 meter and mid section will be 4 meter. So solving this, we will get 12.5 kilonewton as the shear force in the midsection. And if it would have been a straight line, then the midsection ordinate of the shear force would have been 102.5 plus, and minus 17.5 is negative here, minus 17.5 by 2. So averaging this, we will get 42.50 kilonewton. So, and if we just put Vx equals to 0 and solving for that, we will get x equals to 3.055. So the shear force will be 0 at distance 3.055 meter from the point or joint B along BA. So this is also find out. So at 0 shear force, we have maximum bend moment. It will be find out later. So this is the way we can calculate shear force. Now we can easily draw the exact shear force diagram here. So this is the actual shear force diagram that can be plotted here. So all we need is to make the adjustment in the section AB. Other sections have been correct. In the section AB, we just find out the orientation of the curve, square parabolic curve. We just find out the square parabolic curve. So here the ordinate, so at x barabar 4 from the section A or B at midpoint, we have the ordinate of 12.5. We have just recently determined we have ordinate 12.5, and if it would have been a straight line, the average ordinate of shear force would give us 42.5 kilonewton. So 42.5 kilonewton is upward, and you have 12.5 in a below that. So the curve shall be moving from the below direction as shown in a figure, and this magnitude of 12. And this curve changing point will be at a distance of 3.055 from the point B as shown in a figure, and all the else thing are drawn as per previous part. Now for the calculation of bending moment diagram, so we need to assess the ordinates, or that is the magnitude of different moments in the sections, that is at the joints of each sections. We need to assess or determine the value of the bending moment. So in section AB, as there is a triangular load, we have to find different features in this triangular load section. So we cut, as in the case of shear force, likewise we cut a section similar as the shear force diagram, the shear force section in shear force diagram in section AB. Of here we cut the section and we need to determine the value of bending moment M at the section P. So the so moment at X we will find out. To find this, we have taken the summation of moment at point P equals to 0, taking clockwise direction as positive. Here the moment, so we will get moment at X minus 17.5 into X. So 17.5 into X is making anti-clockwise sense, so negative here. And this, the intensity, the triangular intensity loading is giving you a clockwise sense at point P, so it is positive here, positive, plus half 3.75 into X is the height, into X is your the length, into 1/3 of axis. Since from the point P there is a perpendicular portion, so we have to take 1/3 of the total distance X minus 180. So here 180 is your anti-clockwise moment, so that is negative here, equals to 0. And if we solve this, we will receive mx equals to 17.5x minus 0.625x to the power 3 plus 180. So after finding this expression, we can determine the value of moment, bending moment at section AB, that is at the section midpoint. So midpoint of AB, taking x equals to 4 meter, we will get MAB mid equals to 210 kilonewton meter. Likewise, if we put the value obtained in the shear force, that is x equals to 3.055, then we will get the maximum bending moment as 215.64 kilonewton meter in the section AB. So the maximum bending moment will occur at the section where your shear force is 0. Likewise, we can determine the moments in the section BC. Here the section BC is your UDL, uniformly distributed load section. So we just got the section at point P as shown in figure, and assume the moment at that point P as anticlockwise mx. So we need to know the moment at this section mx. So we just applied the summation of moment at point P, caught portion point P equals to 0, and taking clockwise as positive, minus mx plus 180 minus 25 into x minus 10 into x by 2 equals to 0. So solving this, we'll get mx equals to 180 minus 25x minus 5x to the power 2. So the moment in section BC at midpoint, that is midpoint is your x equals to 2. When you just substitute this, we will get moment at section BC, that is mid section, as 110 kilonewton meter. Likewise, in section C, as there is an internal hinge, so we have the moment at C, bending moment at C. We have the bending moment at C section as 0. Now, likewise, in section CD, we have moment at D is 65 into 4 equals to 260. So 65 into 4 is making you, it is giving us 65 downward into 4. So this is giving you anti-clockwise moment. So minus 260 kilonewton meter will be the actual moment. So moment at D from section CD. Likewise, in section DE, we have 40 into 3. That is giving you clockwise moment. So clockwise moment we have. So at section D, we have moment at D equals to 120 kilonewton meter, and at section DF, we have MD equals to 1 minus 140 kilonewton meter. So at section F, we have minus 140 plus 17.5 into the distance is 8 meter equals to 0 kilonewton meter. So our solution is correct. So after doing this, we need to draw the diagram of bending moment diagram.
So friends, this is the way you can just draw the free body diagram of this section, and in this the moment have been balanced, and we need to do the bending moment diagram. We need to make BMD. Here I have written the 180 so red in, so the moment at the joints have been written in red colors and some in black colors. So this has this indicates their individual meaning. As in the red color, the moment is the balancing moment. So actually at joint B in section AB, the moment is taking place as a clockwise, but to balance this moment has been taken as anti-clockwise 180 kilonewton pointer. So this is the balancing moment. So this shall be taken as the opposite direction as it been, like it so it is actually anti-clockwise here. So we need to take it as a clockwise while drawing it. Okay. Likewise, at section BC, we need to take the exact moment that it is clockwise, so it is it should be taken as clockwise. Likewise, in section CD of D, it shall be taken as it shall be taken as your in opposite sense because it is in red color. Likewise in section D of D it should be opposite one, and in X section DF of joint D that should be 140 kilonewton anti-clockwise. So friends, we need to know we need to just make the skeleton of the frame structure here at first. So friends, first you have to locate the various moment that you need to draw. Here at joint A, at A we have, since it is a hinge support here, then moment shall be 0, we need to know that, and it's a triangular section, and triangular load is there, that is UVL, and we have just recently determined the member forces in section AB. Here we have determined that at x barabar 4 at this section you have 210 bending moment. So let us suppose that 210 is here, and at x barabar 3.055 from this B, so we have the bending moment of, so what we have the bending moment of 215. So 215, let us look at this, 215.64. so we will locating this 215.64 here. Now at this is your 180 anti-clockwise movement, so this should be drawn clockwise here, and that should be positive. So 180 is your here, okay, so 180 kilonewton meter. So now this shall be joined here, now this shall be joined here, this shall be joined here, okay, so this is like this, okay. Likewise at BC we have moment of 180 kilonewton, okay, 180 kilonewton meter, and at point C we have a 0 moment, okay, since it is an internal hinge point, so this should be 0 here. Likewise you have to know that this is a 0 moment hinge point, and at the midsection, that is, this is 4 meter and this is a UDL, and you have 110 Newton, okay. So if you join this, so if we join this by, this would be straight line, but it is actually uniformly distributed load. So for this you need to have a parabola here. So this may be parabola may go from this section or this section, so this can be only assessed by the midpoint. So 180 plus 0 by 2, 90, so you have 90 midpoint here. Likewise if we determine here, we have already determined that section BC the mid moment is 110, so 110 lies above and this 90, so there this must be passing from this way. So this is the curve of this section where you're at 10 there is 110 bending moment. Likewise in section CD you have 260 kilonewton meter, you have 260 kilonewton meter, and this 260 kilonewton meter, this 260 kilonewton meter is actually its balancing is clockwise, but we should draw it anti-clockwise, so 260 shall be here, okay. This is not the one commencing line, this is a very different line. So this is 260, and this shall be negative here, this 260 negative here, and this is positive here, okay, and this is also positive here. Likewise at DE you have 120, 40 into 3, 120, that is anti-clockwise, but you have to draw as clockwise, okay. Sorry, 120 is your, what is this, anti-clockwise. So from this 40 into 3 is from draw, this is actually what, 40 into 3 is your clockwise moment. So you have drawn balancing it, 120 is anti-clockwise. So from right side, if you clockwise is taken as negative, isn't it? From left side clockwise positive, from if you go from right side clockwise is your clockwise is your negative, so this should be minus 120. Okay, so minus 120 maybe here, so this value is 120, that is negative here again. Okay, likewise this in section DF you have the bending moment of 140 kilonewton meter, in it is in black color, so that is the actual, this is the actual balancing. So we have to just make this thing locate in the diagram here. 140 kilonewton meter is anti-clockwise, so we will make anti-clockwise, so that shall be located here 140, and this is a point load that should be joined with the inclined straight line, so this is the inclined straight line minus, so again this is negative here. Okay, so now you need to make its hatch here. Okay, like this we can make this as hatch sections, and this shall be like this, and this is 260, this whole portion is 260, this is 120, and this section is 140, so we'll just locate this 40 section here, 140 section here. This is your inclined straight line is 140 section, so this again, so this is the bend, this is negative, and this 260% is here also negative, and this is also negative, so this is the bending moment diagram. So friends, if you find this video as useful, you can like and share to your friends, and for such videos stay tuned to this channel. Thank you. We will meet soon in another video.